Hello, I'm Tyler Hayes and I am a current PhD candidate at the Rochester Institute of Technology. Today, I am pleased to present our work, The Role of Selective Replay in Continual Analogical Reasoning. Before I get into the specifics of our project, I want to highlight some of the current limitations of supervised machine learning. First, agents are often trained offline on static datasets where all of the data is available at once. In this setting, the training and testing data are assumed to come from the same underlying data distribution. If these assumptions are violated and a network needs to update on new data, it catastrophically forgets all previous knowledge. Moreover, in humans, previous knowledge enables us to learn new information more quickly via transfer, and humans can reason about their environments to make decisions. We believe neural networks should also have reasoning capabilities, as well as the ability to learn new information over time, which is known as continual learning. The motivation behind this specific paper is that there are two camps of thinking for computer vision problems. On the left, I'm showing some fast-thinking problems, which include things like object recognition, object detection, image retrieval, and speech recognition. Most of these fast-thinking computer vision problems can be solved by just looking at pixel-level information to identify what's in the image and where it is located. However, we argue that it's more interesting in a continual learning setting to start exploring slow-thinking problems. Slow-thinking problems are problems that require more reasoning capabilities. These problems include IQ tests like Raven's progressive matrices, visual question answering, or referring expression recognition. In this paper, we are specifically focused on what we find to be one of the easier slow-thinking problems, known as Raven's progressive matrices. One characteristic of human intelligence that distinguishes us from other animals is our ability to perform analogical or relational reasoning. Raven's progressive matrices have been a standard IQ test commonly used to measure nonverbal reasoning in humans. On the right, I'm providing an example from the Raven dataset of what an agent would be given to solve. Specifically, the agent is given 8 context panels, and among the rows and columns of the panel, there's a specific rule. The agent must then reason about the relationships between different panels in order to determine which choice panel fits in the best final location. In this example, we can see that each row has one of each shape, a circle, a triangle, and a square, and they're all of the same color and size, so we can easily find the correct answer from the choice panels. We started with Raven's progressive matrices to test analogical reasoning, since this problem allowed us to test the reasoning capabilities of agents in isolation. By isolation, we mean that there is no need to process natural language components or overcome severe dataset biases, which are some of the challenges associated with problems like visual question answering. More specifically, we conduct experiments on the Relational and Analogical Visual Reasoning, or Raven dataset. It's a synthetically generated dataset that consists of more than 1 million images and 70,000 associated questions. The most interesting thing about the Raven dataset is that the questions are distributed among 7 unique spatial configurations shown at the bottom of this slide. There are configurations that include things like a single object in the center of an image, or 2 objects that have some type of relationship between them, such as outside or inside of one another, to the left or to the right of one another, up, down, or even configurations that consists of multiple objects in a grid-like pattern. Each of these different configurations requires unique reasoning capabilities. Since each configuration looks different and requires different reasoning capabilities, this creates a non-stationarity. So we use these configurations to define tasks in our continual learning setup. We depict more about our training protocol here. First, we allow the agents to perform a pre-training phase on the first task, and then each of the remaining tasks is learned one at a time. We study both batch models and online streaming models. Specifically, batch models are given an entire task at once, where all of the images and questions pertaining to the task are provided, and the agent can loop over the data as many times as it wants to learn and update. It is then subsequently required to make predictions about that particular task. We're more interested in the online streaming learning case, where the agent learns tasks one at a time, but it learns samples from within those tasks sample by sample. For example, given the first sample from the center task, the streaming learner would learn the sample and then it could be immediately evaluated. Our experimental setup is as follows. First, we extend the relational base architecture from ECCV-2020 that was designed specifically for analogical reasoning. RelBase operates by processing each of the image frames independently using an encoding network, and then it applies a relation network on top to produce scores or predictions about which of the choice panels is most likely the answer. We extend RelBase to include 3 different types of continual learning models. Specifically, we study 2 regularization models, the elastic weight consolidation and distillation models, which both regularize parameters such that they do not change too much. This helps prevent forgetting. We also study a partial replay model which stores data in a memory buffer and then selects a subset of examples to replay at each time step. We also study 3 baselines. Fine-tuning is a model that doesn't use any regularization or replay components to mitigate catastrophic forgetting and serves as a lower bound on performance. We also study an offline upper bound that concatenates all previous data, shuffles it together, and trains a model from scratch. Finally, we study a cumulative replay model which stores all previous data and incrementally fine-tunes on all previous data. In order to evaluate models, we use 6 unique performance metrics. The first is omega, which is model performance with respect to an offline baseline. An omega score of 1 indicates that a continual learner performed as well as an offline learner. We also compute the average accuracy of a model's performance over all time steps. We then compute a remembering metric, which can be thought of as the opposite of forgetting, and a forward transfer metric. We also compute 2 metrics that deal with computational efficiency and memory. Specifically, we compute the amount of memory that the agent requires beyond the neural network and the amount of time it took to run experiments in minutes. Since we have several unique performance metrics, it is interesting to compare them using a spider or radar chart. In this chart, we apply each of these performance metrics on an axis with a point, and then we draw lines between those points to form a polygon. Agents that contain a larger area in their respective polygon performed well on multiple performance metrics. On this slide, I'm presenting the main results. The top row contains fine-tuning models, the middle row contains regularization-based models, and the last row contains replay-based models. On the left of the spider plots are the computational efficiency metrics like memory and time, and on the right are overall performance metrics including omega, average accuracy, remembering, and forward transfer. Our results indicate that the fine-tuning based models are both computationally efficient, but they do this by sacrificing overall performance. The regularization models perform slightly better, but we can see that they're still lacking with regard to overall performance metrics. The bottom plots for replay-based models show nearly opposite trends of the fine-tuning models. For example, they both perform well in terms of overall performance metrics, but they require more memory because they have to store samples in a replay buffer. Since the partial replay model only replays some samples at each time step, it is more computationally efficient than the cumulative replay model. One thing that I want to point out is that all of these models have pretty low forward transfer scores. This indicates that there is still more work to be done in facilitating better forward transfer. Since the partial replay model performed so well, we were interested in exploring more strategies for how to select which samples the model should replay at each time step. This is important for better network generalization and can also lead to better sample efficiency by smartly choosing which examples the network should update on. A common selective replay strategy is to just randomly sample from a memory buffer and replay those samples to an agent. This strategy usually performs pretty well, but we were interested in seeing if we could do better. Thus, we tested 7 unique replay policies in what we call unbalanced and balanced settings. In the unbalanced setting, we use the raw network scores to select samples, and in the balanced setting, we additionally ensure that samples across previous tasks are balanced. We found that the unbalanced setting worked much better than the balanced setting, and all of the methods we evaluated performed better than the random baseline with statistical significance testing. One interesting finding is that the min replay strategy, which replays samples that haven't been replayed in a while, yields nearly a 5% performance boost over just randomly selecting replay samples. Overall, we found replay methods perform the best. However, there's more work to be done in optimizing partial replay performance further. One option to improve performance would be to optimize for the samples directly or optimize for the selection directly. We could also explore the use of a teacher network that would choose samples to replay to a student network. Another option is to use better buffer management strategies. It would also be interesting to explore alternative network architectures by combining some of the architectures from the analogical reasoning community with some of the modular type architectures used in continual learning. We think that this is just the first step in exploring additional continual reasoning problems such as visual question answering or referring expression recognition. In summary, humans are able to continually learn new knowledge and strengthen their reasoning capabilities throughout their lifetimes. Until now, neural networks have been evaluated on continual learning and analogical reasoning tasks in separate environments. We introduced new experimental protocols, baseline methods, and metrics to evaluate continual analogical reasoning on the Raven dataset. We found that replay methods work well for this task, and they achieve even better performance by choosing which samples to replay in an intelligent way. I'd like to thank my advisor, Chris Kanan, for helping with the project, and our funders for financially supporting this research. Thank you for your attention. This work was published at the CVPR-2021 Workshop on Continual Learning and Computer Vision. The proceedings are freely available online. If you are interested in trying our methods yourself, our code is publicly available on my GitHub page. Thank you.